Friends, very good morning. How are you all? I think program is going well, I hope so. And currently, and in the last session, the discussion was about rolling motion, kinetic energy of the translation, kinetic energy of the rotation, and kinetic energy involved with the rolling motion. This was the discussion we had in the last class. Now goals for the class: gravitational field, gravitational potential and gravitational potential energy, interrelation between field as well as potential. Yes, we are all aware that the lesson gravitation is similar to electrostatics, where you had electrostatic field, electrostatic potential, electrostatic potential energy. Here also gravitational field, gravitational potential, gravitational potential energy. Say when you keep a body of mass cm, and similarly if you keep a charge q, we know that around the charge its influence is there. Here also around the heavy mass its influence is there. If I ask you in the second figure, how do you show the influence, means you have to keep a small test charge from the source charge at a distance of small r. Then there we define it as force experienced by unit test charge placed at a distance or units. That force experienced by the charge implies electrostatic field. Same is the case here. I want to know the strength of the gravitational field or intensity of the gravitational field. First of all, field means the region of space around the heavy mass in which its influence can be felt. So, if you want to know the strength of that influence or intensity of that influence at a particular point, we can define it as it is a force experienced by unit mass placed at that point. It is a force experienced by unit mass placed at that point. And field E is defined as, here that field is represented by I. Intensity of the gravitational field, we symbolize it as I. It is force experienced per unit mass, F by m. That is a simple definition of the gravitational field intensity or strength of the gravitational field. It is the force experienced by a unit mass placed at that point. But already in our last classes we have seen F is equal to G m by r square into m. So you came out with the result Gm by r square. So I is equal to Gm by r square is the intensity of the gravitational field. And when you observe this equation, you will find there is a similarity dimensionally, this equation and the relation between small g and capital G. There you had Gm by r square. So dimensionally I is equal to Gm by r square and G is equal to Gm by r square, both are same. And this intensity of the gravitational field is a vector quantity. And when it is a vector, how is the direction? The direction is towards the central body. The direction of the intensity of the gravitational field is towards the central body. So, I is equal to Gm by small r square. I is equal to Gm by small r square. Now, let us see the intensity of the gravitational field due to CMD. CMD, you know, continuous mass distribution. Under this intensity of the gravitational field, we deal with a solid sphere, a spherical shell or hollow sphere, and a ring-like structure. So, these are the CMDs we take under the topic continuous mass distribution. When I take a solid sphere whose radius is equal to Kepler, and let us place a point P at a distance of small r, and it is a solid sphere, mass is distributed throughout the body. In this case, we deal with 3 different points. One point outside, other point on the surface, and a third point inside, and a fourth point at the center O. So, under consideration we are dealing with 4 points: outside, on the surface, inside, and at the center. When you observe that I out, intensity of the gravitational field outside the solid sphere, as we know, Gm by small r square, and when you brought it inside, I mean nearer to this point, means it is on the surface. When it is on the surface, small r is equal to Kepler. So, I on the surface is equal to Gm by Kepler square. Now, you are bringing it into inside. I am dealing with this point, inside point. When it is brought inside, it is given by Gm by r cube into small r. Inside the solid sphere is given by Gm by Kepler cube into small r. Next, this is inside, means from the center to the surface, anywhere you can apply this. Next, when it is at the center small r is equal to 0. So, strength of the gravitational field or intensity of the gravitational field will be equal to 0. This is related to the solid sphere. Outside Gm by small r square, on the surface Gm by Kepler square, inside Gm by Kepler cube into small r, at the center it will be 0. And we can plot a graph taking I on y axis and smaller on x axis. This is the shape of the graph. This graph resembles variation of small g with respect to r. At this point, small r is equal to Kepler, greater than Kepler, less than Kepler. This point is center. So, this is the strength of the gravitational field with respect to the first object, which is an example of CMD called as a solid sphere. Next, hollow sphere or spherical shell means there is no matter inside, it is empty. This will be the figure. Again, we are considering the different points. Our discussion is gravitational field. Here also gravitational field. So, the radius of that shell will be equal to Kepler. Again, outside I out is equal to Gm by this distance is equal to r Gm by r square, I on the surface Gm by capital R square, inside there is no matter, field will be equal to 0 and I at the center is also equal to 0. So, totally when you observe this Gm by small r square, Gm by capital R square, and inside because of no mass, field will be equal to 0, and we can plot a graph taking I on y axis and small r on x axis. This will be the variation of field with respect to distance. This is less than capital R is equal to R greater than capital R. This is with reference to the spherical shell or hollow sphere. The difference between the previous model and this was, their matter is inside, here there is no matter. Because of absence of matter, field is also absent inside. Now, we are taking field due to the another one. A ring like structure. At a point P, and the radius of this will be equal to capital R, and mass of this will be equal to am. So, field due to the ring like structure having a radius of capital R, this will be equal to, when you observe this, for a ring we know that there is no inside matter. So, when the inside matter is equal to 0, as you are well aware that the field will not be there, similar to the previous one where the field is absent inside. So, here let P be the point at a distance of x unit from the center. So, for this Gm into x by r square plus x square whole to the power of 3 by 2. This is the intensity of the gravitational field due to the ring like structure Gm into x by r square plus x square whole to the power of 3 by 2. Say for example, if the point is at the center, if I take P at O x will be equal to 0, then intensity at the center will be equal to 0. Next, if the distance x is very greater than r, means you are considering the point to be away from the object, then you can ignore r and I will be equal to Gm into x by x cube, that is equal to Gm by x square. Now, when you observe this, at which point of the, at which value of the x field will be maximum. So, under this my first question to you, for what value of x, for what value of x field is maximum, let us see. We know that for field to be maximum, we have to take the help of calculus. For a function to have either maximum value or minimum value, the first derivative of the function will be equal to 0. So, here this I is a function of x, di by dx. I want to know for what value of x field will be maximum. So, let us consider the equation of the field and let us differentiate it. So, Gm into d by dx of x by r square plus x square whole to the power of 3 by 2. Gm being the constant, we know that for a function to have either maximum value or minimum value, its first derivative will be equal to 0. So, 0 by Gm anyway will be equal to 0. d by dx of this, it is in the UV format, r square plus x square to the power 3 by 2, derivative of x with respect to x 1 minus x into, it is in the format x power n 3 by 2 r square plus x square whole to the power of 1 by 2 divided by r square plus x square whole square, that will be equal to 0. This is already according to the calculus. So 0 into this will be equal to 0. Then what you will get, r square plus x square whole to the power of 3 by 2 will be equal to 3 by 2 into x into r square plus x square to the power 1 by 2, r square plus x square to the power 1 by 2. So this will be cancelled, r 2 into r square plus x square is equal to 3x. Are you able to follow? So when you get back once again, see, for the function to have maximum value, its first derivative must be equal to 0. So gm into d by dx of x divided by r square plus x square whole to the power of 3 by 2. It is in the form u by v, v into derivative of u minus u into derivative of v. So we have taken x into 3 by 2 r square plus x square whole to the power of 1 by 2 into inner derivative of x square is equal to 2x. So when you take the inner derivative, whatever the main function, again inside there is our function x. Since we are differentiating with respect to x, you have to write the inner derivative of x also. Therefore this will be equal to into 2x. When you observe this term will be equal to 0. R square plus x square whole to the power of 3 by 2 is equal to 3 by 2 into 2x. This will vanish. So r square plus x square will be equal to 3x square. So 3x square minus x square, 2x square is equal to r square. X will be equal to r by root 2. For x is equal to r by root 2, the intensity of the gravitational field will be maximum. At x is equal to r by root 2, I will be equal to maximum. This is about the CMD of this three types of objects. One is solid sphere, second one is spherical shell, and third one is a ring-like structure. Now let us see the numericals based upon the field concept. When you observe the field concept, the problems are more prominent in this. So when you observe the value of this field, problem number 1, numericals on gravitational field. In your electrostatics, you had an equation. One is nothing but principle of superposition. Here also we apply the principle of superposition. Say I am keeping 3 objects of masses m, m, m in the configuration of a square having a side of length a. At this point O, that is nothing but center of the square, I would like to know the strength of the gravitational field or intensity of the gravitational field. So this is the problem. Find intensity of the gravitational field at the point O in which 3 masses having the value capital M are placed at the 3 corners of a square having a side equal to a units. For this you have to apply the principle of superposition. So when you observe the point O, this point O, the field at the point O, this distance will be equal to half of the diagonal, that will be equal to a by root 2. Field at the point O due to the mass at the point A is nothing but, as we had a formula, Gm by square of the distance, a by root 2 whole square, and field at the point O due to the mass B, again Gm by a by root 2 whole square, and again this distance is also equal to a by root 2, this distance will also be equal to a by root 2. Field at the point O due to the mass placed at the point C will be equal to Gm by a by root 2 whole square. So, we have computed the individual fields due to the individual masses at A, B and C. Now, you cannot add them directly. Why? Because field being a vector, you have to take the help of parallelogram of vectors. See, these are the vectors drawn. This is EA and this will be equal to, as I said, the direction of the field towards the central body, this will be equal to EC. So, you have to represent the field with the help of a vector. When you observe that EA and EC are equal in magnitude and opposite in direction, so the field along the diagonal EAC will be equal to 0. So, net field or net intensity of the gravitational field I net at the point O will be equal to, it is due to the B only, that is equal to 2 Gm by A square. This is the net field at the point O due to the mass at the location B. Next, in this now, the masses are arranged in the form of an equilateral triangle A, B, and I want to know the strength of the gravitational field at the point C. Let A be the length of the triangle, side of the triangle, which is considered to be an equilateral triangle. The field at C due to A, IA, the masses are having value mm, Gm by A square, and field at C due to the mass at B is equal to Gm by A square. So, the vectors will be like this, and the angle between them will be equal to 60 degrees. Then net field at C is equal to, you have to apply the parallelogram law. According to that, root of p square plus q square plus 2pq cos theta. Applying that, IA is equal to IB is equal to, for example, I. So, what I can write? I square plus I square plus 2I square cos 60. Cos 60 value 1 by 2. This will vanish. That will be equal to root 3I square. I net will be equal to root 3 into I. That will be equal to root 3 into G m by A square. This is another model in which the masses are assembled in the shape of an equilateral triangle. Now, the more prominent problems are nothing but contest time. Direction of the gravitational field intensity is towards the central body, away from the central body, axis of the earth, that is nothing but central body, none. This is a contest question. Now, summary of the class, we discussed with gravitational field, gravitational potential energy. Now, gravitational field we have done, and let us observe the gravitational potential as well as potential energy. It is again similar to the electrical potential. Here we are calling it as gravitational potential. The gravitational potential at a point is defined as, see how the definition can be applicable for problem solving. The gravitational potential at a point can be defined as work done in bringing, what is it? Work done in bringing unit mass from infinity up to the point under consideration. So here the symbol for potential, similar to the electrostatics, we designate it as V, is defined as work done, W, in bringing unit mass from infinity up to the point under consideration. Say for example, this is a source mass having a value m, and this is the point P, and your test mass m is at infinity, and I would like to know the gravitational potential at the point P due to the source mass m. For that I am performing a work. What for I am performing the work? To bring that unit mass from infinity up to the point under consideration. And whatever the definition we had, we have given the mathematical representation. V is equal to W by M. Work done. Work done is nothing but force into displacement. That is nothing but minus F into displacement R by M. That is nothing but minus G M by R square into R by M. MM gets cancelled. So potential at that point is given by minus Gm by R. The work done against the gravitational field, you are performing the work against the gravitational field in bringing that unit mass from the infinity, means from a long distance point to the point under consideration. So when you observe this, potential is always considered to be negative. Highest value of it is 0, that will be available at infinity. And when you observe this, potential V is inversely proportional to the distance R. Now what is the difference between the potential as well as potential energy? Potential energy is defined as work done in bringing entire mass. Here if you keep the mass as a unit, it is called as potential. If you treat that entire body mass from infinity to the point under consideration, we call it as potential energy. So potential is different, potential energy is different. Then as per the definition, potential energy, how do we say mathematically? The symbol of potential energy will be equal to U. That is nothing but potential into mass of the body. Potential into mass of the body is called as potential energy. Whatever the work you are doing in bringing the body from infinity up to the point under consideration, that will be stored in the system as a potential energy called as a gravitational potential energy. So by putting the mathematical expression for it, potential at that point is minus Gm by R. M being the source mass, R being the distance of that point from the central body. So minus Gm by R into M. So potential energy at that point is equal to minus Gmm by R. So this is the difference between the potential and potential energy. In our numericals, we have to assemble potential energy for triangular structure as well as the square like structure as well as cube like structure, and we have the problems. What is the work done in increasing the length of a square having 4 masses from A to 2A? These are the models where we can come across related to the topic potential and potential energy. For example, if you take a 2-particle system, the distance is R, this mass is equal to m1, this mass is equal to m2. Then the potential energy of the 2 particle system is minus G m1 m2 by r. This is for a 2 particle system. When you take the 3 particle system in which the masses are assembled in the form of a triangular like structure. So, these are the masses configured in the shape of a triangle. The distance between m1 and m2 is r1 and m2 m3 is r2 and m3 m1 is equal to r3. I want to know the potential energy of system of 3 charges configured in the form of a triangle. Then total potential energy for this is U dash is potential energy between m1 and m2, U1, potential energy between m2 and m3, U2, potential energy between m3 and m1, U3. Total potential energy of the system is U1 plus U2 plus U3, that will be equal to minus G m1 m2 by R1 minus G m2 m3 by R2 minus G m3 m1 by R3. So, this is a system of potential energy for 3 particles assembled in the form of a triangle. So, once again the brief recap of the session: gravitational field and gravitational field for different types of configurations, then gravitational potential and the definition of the potential and the mathematical representation, and the gravitational potential energy of 2 particle system, 3 particle system. In the next session, we will see the relation between the gravitational field and potential similar to the electrical field and electrical potential, and we will come across with some examples. Thank you for joining. Have a nice day. Thank you all.